Today we are going to be starting the pressure half of our unit in the Unit 5 packet. So you can find these notes on pages 21 and 22 in your unit packet. If you happen to hear my dogs in the background, I apologize, but it's nearly impossible to keep them quiet for more than, like 2.5 minutes at a time. So you may hear some of them barking out the window downstairs. So for right now, we're going to kick it off by discussing what I call just the generic kind of mechanical view of what pressure means. In other words, in physics, when we say pressure, what are we talking about? It does include force, so we are talking about force again, and it's how that force interacts across a surface. So how spread out does that force get as it's being applied to a certain object or to a certain surface? And so the definition that we get for what pressure means comes directly from the mathematical relationship. It's the force that's acting on that surface divided by the area of the surface across which it acts. So in our equation then it's just P for pressure equals F for force divided by A for area. And your force in this case would be measured in newtons still, just like we've done all year. Your area would be in square meters, and then the units for pressure are named after a scientist. They are pascals, named after Blaise Pascal. It's a name that you might recognize from chemistry potentially if you've talked about him. The abbreviation for Pascal is a capital P with a lowercase a. And so 1 Pascal is therefore equal to 1 Newton divided by 1 square meter. And now if you think about the size of 1 square meter, 1 meter stick long by 1 meter stick wide, that's a pretty large square area. 1 Newton is not a whole lot of force. Ironically, this ends up being about the weight of 1 apple spread out across 1 full square meter. So when we see pascals, we're oftentimes going to see numbers that might be larger, sometimes even measured in thousands of pascals or kilopascals. So that means that we're going to have to be a little bit comfortable seeing some larger numbers in our calculations and things as we go through those. Now, because the Pascal is dependent on square meters, this means that your area has to be in square meters. So there are times where we're going to have to convert things that might be given in square centimeters or even square millimeters and get them to square meters. Now, the conversion, because the units are squared, does come down to being a little bit more tricky than what we're used to with our linear measurements. So there's 2 ways that you can kind of think about this, and it depends on how the situation is given to you. The easiest one, which is probably the most intuitive thing to do, would be if they give you the dimensions of the area, you would change from millimeters or centimeters into meters before you even calculate the area. And this would then use our 1 meter is 100 centimeters, which is 1,000 millimeters, as our base units of conversion there. That's what we've been familiar with throughout the years, those linear conversions. So as we do it now, if you can change the dimensions before you calculate it, then you can use that same very familiar conversion. You move the decimal point 2 places to get from centimeters to meters, or 3 places if you're going from millimeters to meters. Unfortunately, most of the time, we're not going to have that opportunity. It's rare that they're going to give us an area that is already labeled by dimension. Instead, they're going to just tell us what the total area is. And in that case, we're going to have to go from potentially square millimeters or square centimeters into square meters and stay in those squared units. And the conversion factors then end up being a little bit strange because of the larger numbers and values we have to use with those squared units. And here's how it comes out. The easiest way to describe this is to actually think about having a 1 meter by 1 meter box. So if we actually laid this out and we measured it 1 meter on each side, then we know from math that the area of that rectangle is length times width. 1 meter times 1 meter is just 1 square meter. So that's a very straightforward way of being able to calculate that. Now, if you think about changing the dimensions of that rectangle, we're not changing the physical size of it, but we're changing the units we use to measure the dimensions. So we go to centimeters. So we have 100 centimeters by 100 centimeters on our sides. And that means then that your area becomes 100 times 100, which ends up being 10,000 square centimeters, which is the same as 1 square meter because it's still the same box. And then likewise, if we go to millimeters, well, 1 meter is 1,000 millimeters by 1 meter on the other dimension is also 1,000 millimeters. So again, all three boxes are the same physical size. We're changing just those linear units. And now the area in square millimeters is going to be 1,000 times 1,000. That gives us 1 million square millimeters. So in summary, 1 square meter is the same thing as 10,000 square centimeters, which is the same thing as 1 million square millimeters. So we have different conversion factors that we have to think about now. If you don't like the larger numbers, you could also use powers of 10. 10,000 would be 10 to the fourth, and 1 million would be 10 to the sixth. Now, many of you probably would just rather use the larger numbers. Totally fine. Yeah, you can do that. But these exponents are telling you how much you'd have to move the decimal point. So for example, if you're moving from square centimeters to square meters, because it's the squared units, you have to go 4 places with the decimal point, rather than when we just had linear centimeters measuring a straight line and linear meters, then you had to go just 2 places for those. But because of the squared units and how we calculate area, that's why we're deriving it this way, to show you that it's not the same relationship between the square meters, square centimeters, and square millimeters as what we might be used to. So pay attention to that and be very careful with that in the case where we might have to convert things. And come back to look at the diagrams. You just think about those boxes being the same length, and it does help break that down a little bit more. If we turn the page over to the back, we're going to talk first, before we get into calculating things, a little bit about the conceptual side of things. There's a lot of concepts that we can talk about with pressure, and we will do that as we go through this part of the unit. One of the first ones that we can talk about is a famous magician's illusion, where you see a person that can sit or lay down on an entire bed of nails, and the nails are very real, very sharp, but yet they're okay with that, and it doesn't hurt them, it doesn't puncture their skin. And so we're going to ask, why is it possible for one person to sit on an entire seat of nails that might have, 600, 700 nails on it, but why would you never want to sit on just one nail? Well, the concept of pressure helps us to be able to describe what's changing in that situation. So if we envision that we have one nail, okay, this is just one nail, the tip of this nail is very small. So the very, very point of that nail has a very, very small area to it, a very small surface area. So if you put much force on that very small area, it's going to hurt. It's going to puncture your skin very easily. You don't even need to put a lot of force on it. But if you take, instead of one nail, and you put that together with, let's say, almost 100 nails, now you have the surface area of all of those points that come out on that block or bed of nails. And so even though these are very sharp nails still, you can actually put a lot more force on that and not increase the pressure to the point where it would actually puncture your skin. Now this little demonstration is actually used to show that idea with a balloon, and I'll have to do that in a separate video of demonstrations a little bit later on. But for right now, you can understand the idea that if you spread out somebody's weight, not on just 100, but you need more than this, but if you spread out a person's weight or their force across a whole seat of nails, you have increased the surface area that that person's force or weight is acting on, and therefore distributed that weight in a way that the pressure is not high enough to break through their skin. So if we were to actually put that into words as an explanation, their weight is spread out over hundreds of nails, so the surface area, I'm going to abbreviate here, SA for surface area, is much greater thus reducing the pressure. And it's the pressure that's the measurement that's going to dictate whether or not those nails will puncture your skin. So the pressure, not the force, but the pressure is what's determining whether or not your skin will break through. And in fact, that's a common theme that we're going to see in some of the other examples that I'll later show you, is that the pressure determines when things break, or maybe when you might think of it as things hurt. It's not just the blunt amount of force that's important in determining those things. So then we move on to our second situation here. If anybody's ever done this, although I don't know why you would wear high heels and deliberately walk across mud, but sometimes it can happen just incidentally. But if somebody is wearing high heels and walking on soft ground, whether that's mud, potentially even like snow or things like that, and they'll sink in, right? They sink into the ground. And if you were walking on just a flat bottom shoe or tennis shoes, things like that, you might notice people not having any trouble with that ground at all. So what's the difference? Well, of course, a high heel, if you think about the actual bottom surface of that shoe, is much smaller surface area than if you had a tennis shoe. And the bottom of that shoe, the sole of that shoe, would have much more area. So you're taking the same amount of force and you're putting it now over a smaller area. That means that you have a higher pressure, and that pressure then will be what results in sinking or pushing into the ground in those situations. So why is it a bad idea? Well, the heels are where you're going to have the most weight and also the smallest area.